and thanks everyone for coming to our seminar. I will turn off my video shortly so that we can all focus on the slides. So let me actually do that right now. So the subtitle of our topic is adapting portfolio optimization to market regimes via machine learning. And so I'll start by talking a little bit about market regimes, because to understand why this method works, it is essential. Market regimes plays a very important role on why this particular portfolio optimization technique works better than the traditional ones. So many of us who are in finance are familiar with these regimes: bull market versus bear market, a flat market versus a choppy market, risk on versus risk off, inflationary versus deflationary, and etc., etc., etc. These are well known, and because they are visible, anybody in retrospect can identify them. They may not be able to predict them, but at least they know which regime we are in right now. And these regimes also affect broad market indices. It is not just your portfolio or my strategy where they are important. It is for really regimes that are applicable to the broad market index. But there's one characteristic that make them particularly perhaps useless for portfolio optimization. They are very easy to identify after the fact, a posteriori. So you can say, well, in the past 6 months, we are in a bear market. Well, anybody could see that. Just look at the Yahoo Finance. But who can really predict it in the beginning of those 6 months, right? Because if you can predict that we are in a bear market in the next 6 months, in a bear market regime in the next 6 months, you wouldn't need to do anything else. Just bet on the index future. So identifying these kind of visible regimes can be as hard as predicting market directions. And generally speaking, machine learning are not very good at that, because if they are good, we wouldn't all be still struggling in finding best way to apply machine learning. We should all just become traders. And in fact, Google and Facebook would be the biggest hedge fund if it were so easy to use machine learning to predict market directions. Now, what are more interesting are what many people would call hidden regimes. An example would be, and a hidden regime really is the answer to the following typical question: why is it that my strategy or my portfolio are suffering a drawdown when the market is bullish and calm and optimistic, right? So many portfolios and many hedge funds suffer big losses in, for example, 2021. But 2021 had been a great year for equities. Why is it that so many market neutral funds were not doing well, and some of the long short funds actually closed down shop in the first few months of 2022 after a very bad year? These are probably due to hidden regimes. Now, you might speculate, is it because the retail traders are buying call options on meme stocks like GameStop? Is it because they are big family office like Archegos? They are liquidating because they make some wrong bets and lead to contagion? Or is it because of some complicated non-linear combination of market and macroeconomic factors? It is very hard to discern. It's not so often easy to identify exactly why a strategy is suffering. Interestingly, however, it is often easier to predict. So we have a contrast between visible and hidden regimes, and for one which is easy to identify, hard to predict, and the other one is hard to identify but easier to predict. Why are they easier to predict? Well, it is easier to predict, first of all, because these hidden regimes may be applicable only to some specific strategies. Not everybody are trading the same strategies. We are not talking about these hidden regimes that are applicable to the broad market index. And so they are less subject to arbitrage. Whenever something is less subject to arbitrage, it's easier to predict. And secondly, many of these strategies, unlike market indices, have specific factor exposure. That's something that many people in finance are familiar with. For example, if your strategy short volatility, it is clear that when the market regime is in a state where the volatility is increasing, it is unlikely that a short volatility strategy would do well. On the other hand, if your strategy is long volatility, like many of the tail hedge strategy or crisis alpha strategies that, by the way, I have been running for many years, you can see that if a market regime is very volatile, full of surprises, whether it is from war or from inflation or political turmoil, it's very, it's a kind of no-brainer to say that, well, this would have positive factor exposure to tail risk, and this strategy should do well in the current regime. And moreover, it is likely that this kind of regime will continue for a while. So it is predictive. It's predictable, I should say. Unlike whether you are predicting bull or bear market, which can change at 12 o'clock today or 1 o'clock today, whether the market is full of surprises, whether it's full of tail risk, typically lasts for a while. And so, and here's the important key assumption is that many of these successful regime predictions depend on the low frequency of regime changes as compared to the frequency of trading. If we are talking about regime change that change every 5 minutes and your trading frequency is also 5 minutes, predicting regime change is as difficult or as easy from your point of view as predicting market direction at that interval. But that's not the case. A lot of times regime change at a much lower frequency than the frequency of your trading, and or the frequency of your portfolio rebalancing. That's why regime predictions are important for our applications. Now, what are the traditional methods of regime identification? Well, typically state space models in general, or hidden Markov models specifically. Now, these models are very weak because they typically use only past historical prices or returns as input. They do not really have the capability of taking into account the broader macroeconomic or market features. Now, I see there's already a question. As I said, please feel free to ask any questions while I talk. We don't have to leave it until the end, and I will occasionally definitely look at the questions. So yes, Salem asked, it's not really a question, it's a comment. So he said that he used a random forest classification to predict regimes. That's great. Okay. Now, what can machine learning help in this respect? As I said, traditional state space models are very weak. Well, machine learning obviously can take into a much larger pool of predictors, what are called features in the field, and they can include any number of factors that you can dream of, global economic or market variables, or even unstructured data such as sentiment scores, unstructured text from Twitter and other social media could also be an input. And more importantly, however, is that it can also handle nonlinear interactions of these predictors, unlike many traditional factor models. So here we have a system, a known technique that can take care of many of the deficiencies of traditional models. And one example where regime prediction was actually quite successful is to apply. It's called jump models. It is kind of a generalization of hidden Markov model, except that it allows many input features from far away from simply using prices or returns as input. And I have cited this paper where there was a fairly recent paper it was published last year where they had some notable successes. Now, what we are doing, however, is not to directly identify hidden regime. We use hidden regime as an explanation of why this methodology works. We do not actually need to build a regime prediction model for it to work. So let me explain what this optimization method in one slide. So what we want to optimize is very simple. It's a future return or future Sharpe ratio. Okay, maybe 1 month Sharpe ratio or maybe 5 days return. That's what we want to optimize, right? This is very understandable. It's the one period optimization problem. We are not doing a multi-period, long horizon optimization. Maybe 1 month on 1 week, or even 1 day if you wish. What are the input to this optimization? The input to optimization could be anything, market and macroeconomic variables, but most importantly, it includes strategy or portfolio parameters. That's why we call it conditional parameter optimization. Most often, and I think that is one of our key insight, is that most often machine learning uses variables that are external as features. What they are omitting are variables that you can control. You can definitely use parameters that you can control and add that as part of the feature factor for the machine learning prediction model. Where are the hidden variables? Well, we don't have, since they're hidden, we don't have to explicitly identify them. In fact, they are represented by these features, these market and macroeconomic features. They are representing the hidden variables. Very good. Where is the optimization? Well, once you can accurately predict the target variable, such as future return, naturally, you can vary these input parameters and find out what will give the best return or best Sharpe ratio. That's the optimization search. So naively, you can run an exhaustive search for parameters that can predict the future maximum future return or maximum future Sharpe ratio. That's the naive search. Now, in practice, when your parameters become numerous, that is not practical. But let's assume that we only have a strategy. We have a strategy with only 2 parameters. A simple strategy. Let's consider this toy strategy called a Bollinger Band strategy. It is a mean reverting strategy on a ETF pair. A GLD is a gold ETF, and GDX is a gold mining company's ETF. And we consider this portfolio consisting of these 2 ETF as a mean reverting portfolio. We have a hedge ratio that determines how much to invest in one versus the other. Another parameter is the entry threshold. In a Bollinger Band, you can decide, do you want to enter into a position in this pair at 1 standard deviation or 2 standard deviation or what? And also there's another parameter called the look back, which is the moving period where you determine the average and the standard deviation for this spread. This is a typical example in pair trading, and it has only 3. Actually, it's 3 parameters. I misspoke. I originally said it was 2 parameters. It's actually 3 parameters. How do you optimize the hedge ratio, the entry threshold, and the look back in order to get, let's say, the best Sharpe ratio? Well, in the setup would be, using machine learning would be simple. You first use these 3 variables. Let me highlight them. As part of the feature factor, you have the hedge ratio, the entry threshold, and the look back. So these are the 3 variables that you can control. And then there are, of course, other market features. You can imagine money flow is one, and the C-score of the individual instrument might be others, and many. It could be hundreds of them. In fact, PredictNow has created hundreds of market features that are, can assist any sort of optimization problem that our clients can come up with. But most importantly, these features cannot be changed because they are external to the problem. They are given to you by the market. But these variables, what we call the control features, you can change at will. You can backtest any number of strategies based on different hedge ratio and different entry threshold, and present that as training data to the machine learning model. And that is the key. You will be able to create as much training data as you like by trying different combination of these control variables, as many as you like. And once the model is trained, presumably it can be able to, it can predict accurately, given a certain set of input parameters and given a particular set of market features, what is the expected return or the expected Sharpe ratio going forward for this strategy. And actually, this toy example is in the first paper that we published, and it was successful. It's a toy example, but that method proved successful. It generated a better Sharpe ratio than if you are using traditional optimization or walk-forward optimization method. But that's not what we are talking about today. We are talking about a much more complicated problem. What if we are using this method, applying this method to portfolio optimization, where the trading strategy is a portfolio of many, many components? We could be a portfolio of stocks, could be a portfolio of futures, bonds, forex, or even a portfolio of strategies, of trading strategies. In this case, the so-called control parameters or the trading parameters are the capital allocations to the individual components. You can imagine the number of parameters become explosively large. If you have a portfolio of 1,000 stocks, you potentially have 1,000 parameters that you want to optimize. And so what we were successful with this exhaustive search of 3 variables, combination of 3 parameters, will no longer be possible because we now have hundreds, if not thousands, of variables, of which there could be astronomical number of combinations to try in your optimization problem. So we are faced with a curse of dimensionality. And one of our major contribution is how to solve this curse of dimensionality. That's why we have a number of mathematicians on our team and optimization experts on our team. And because of their hard work, not because of my contribution, it's our team's contribution, we're able to overcome this curse of dimensionality. And so that's really what's the major contribution that we have made in this problem. So I'll talk a little bit further about portfolio optimization and what are the successful use cases of this strategy. Okay, so in traditional portfolio optimization method, you must be familiar at least with 3. One is risk parity. Sometimes it is also known as inverse volatility portfolio. It is very simple. You assume that there are 0 correlations of returns among the constituents of the portfolio, and you allocate capital based on the 1 over their volatility. And what that means is that you are trying to allocate equal risk to each component of the portfolio. Each component of the portfolio are contributing equal risk, assuming that the risks are uncorrelated. Obviously, it's the wrong assumption, but that's a very typical kind of portfolio that people present. Of course, even more naive allocation is equal weight. But that's hardly an optimization method because you're not doing anything. You are only allocating capital to equal weights. But you'd be surprised how many professionally run portfolios are based on that optimization method, a non-optimization method, which is equal weights. So risk parity is already 1 leg up on the most naive or most common method of allocation. It actually does something. It actually does some computation by making sure that it is contributing equal risk. Now, if you take it to the next step, you are going to incorporate covariances of returns. That will take us to the Markowitz method. You are dealing with a minimum variance portfolio where you are minimizing the portfolio volatility, assuming non-zero correlation. And in the following figure, it is a typical efficient frontier diagram that you would learn in every portfolio management textbook. You will see that the minimum variance portfolio is this point, is the black spot here. This is the MV, what we call MV, the minimum variance portfolio. It's at the edge of the efficient frontier. It has the lowest variance of all the potential portfolios looking backward. Again, we have to emphasize this is not predictive. All these conventional portfolio optimization are not predictive. They are looking historically in the past, and they find a portfolio that happened to minimize the overall variance of the portfolio, assuming that all that matters are the past expected returns and the past covariances of returns of the components. Standard finance stuff. Then, of course, there is the Markowitz portfolio, also known as the mean variance optimization. This is very similar to the minimum variance portfolio, except that we are now not minimizing the variance, but maximizing the Sharpe ratio. And if you're referring to the efficient frontier, that red dot would be the maximum Sharpe ratio portfolio. Some people call it the tangency portfolio, and that is the result of Markowitz portfolio optimization. That is typically the portfolio that a finance professor would tell you to adopt, whereas typical industry practitioner would ask you to adopt the minimum variance portfolio or even the risk parity portfolio. Okay, but these are all traditional methods, and the key is ingredient is that they only use past expected returns of the individual component as well as the covariance of returns as the input. No larger context are included. No larger macroeconomic contexts are included. No regime information are included. It is assumed that whatever worked in the past is going to work in the future. Well, your financial advisor would have told you past performance is no guarantee for future results, but they are swept under the rug, ignored in this kind of academic portfolio optimization method that are actually being practiced by many industry practitioners in many funds. So, as I said, none account for regimes. So you might say, well, why don't we optimize it using a walk-forward optimization method? Just use one last year of the market conditions of the returns, so that we can supposedly adapt it rapidly to the changing condition. Well, that doesn't work, because if you were adapting this portfolio optimization to, let's say, the condition in 2021, they could hardly be more suboptimal than the condition in 2022, right? The market, changes. The market direction changes drastically from one year to another. There's nothing in common really between 2021 and 2022. So whatever that was optimal in 2021 could hardly be less optimal in 2022. So walk-forward optimization usually doesn't work very well, in combination with this kind of portfolio optimization method. So our goal really in saying that this is conditional portfolio optimization is that we want to find the optimal portfolio for the future, not the optimal portfolio in the past. And to do that, we need an implicit prediction of hidden regimes. And as I said, these implicit hidden regimes are represented by macroeconomic and market features via machine learning, and using that to predict the future. Now, you might ask, what are the, what are the features? What are the ingredients? Well, to be more detailed, of course, we would use time series features from the stock market, such as the Fama factors, such as stock fundamentals that are transformed into time series features. We could use options market features. We can use market indices, such as implied correlation, implied volatility indices. We can use specialty ETFs returns. We can use global futures. We can use Forex, whatever that you can think of. But, and we have, a paper that describes all these different features that we have created to enable the success of CPO. But at a high level, what's important to understand is, why is it that this method works? Most notably, no cross-sectional features are used. We do not need individual stock return. We don't need to predict individual stock return for this portfolio to work. Because in a lot of machine learning approach to portfolio optimization, that is actually the key, is that, well, we didn't know what was the, we know that past returns is not predictive of future return. But what if we can predict future return? So what they do is that they create a machine learning model to make return prediction for each component of the portfolio, whether the component is a stock or future. They're making cross-sectional predictions. Well, needless to say, that is very hard. If you are actually good at cross-sectional return prediction, you don't need portfolio optimization. You should just be a stock picker. if you can predict that, Tesla is going to go up 5% next week, whereas GM is going down 3%, you can use that information to directly make a pair trade or make it into a stock selection model. You hardly need to be so indirect and use that for portfolio optimization, because your whole portfolio construction can be based on this kind of cross-sectional return prediction. But the problem is cross-sectional return prediction are very hard. And so we are avoiding it completely. This particular method of conditional portfolio optimization does not use any cross-sectional features. They are only using what in the industry called time series features that are global, that are not specific to individual stocks or the individual futures or individual component. The classical analog of this advantage is that we are using, for example, three-factor. If you're thinking about how to understand this, we are essentially using the machine learning equivalent of a three-factor Fama-French vectors to predict portfolio return. Imagine you have a portfolio of 1,000 stocks, and Fama-French would be only using 3 variables to predict what their returns are. It was never very accurate, right? It can't have any significant R square at all. And traditionally, it doesn't work very well in most contexts. You can't use that for any decent portfolio stock selection or even the portfolio allocation. But how do we make it work in the machine learning context? Well, not only because we are using many more factors than the three-factor Fama-French factors, and not only because we are taking into account nonlinear interactions between the factors and not just the linear combination of these factors, but also crucially, we don't need to predict portfolio returns accurately for this optimization problem. That is one of the key advantages. We only need to accurately predict the rank. We only need to rank the portfolio returns accurately. We do not need to predict them accurately. And there's also a classical analog of this, where only ranking is needed and not actual magnitude prediction. And that is where people would use a factor model to rank stocks to form a long-short portfolio. So, if you are if you study a lot of the classical finance literature, to create a long-short market-neutral portfolio, you can use any number of factor models and use that to rank the stocks and long the stocks that are expected to have the highest return and short the stock that are expected to have lowest return. But again, the actual return predictions do not need to be accurate. All you need to do is to rank the stock's return accurately in order for this portfolio to generate positive alpha. The difference with our approach is we are not even needing that to generate long-short portfolio. We are using that to pick optimal portfolio. We are using the ranking that is generated by the machine learning model to pick the optimal portfolio and not forming a long-short portfolio, because we do not believe that even picking the stocks are necessary. We don't want to be selecting stocks. We are only good at finding out whether that portfolio has the best capital allocation or not. And to do that, we only need to rank different capital allocation accurately and not to predict the outcome, the forward return or the forward Sharpe ratio accurately. And that contributes to the success of this method. Now, when I keep saying success, what are the successes? Here we are. We can talk about 5 different use cases of this methodology. One, S&P 500 portfolio, we backtested it out of sample for 1 month Sharpe ratio prediction for about 10 years. The Markowitz method, if you apply it to S&P 500 portfolio, give a Sharpe ratio of 0.31. The CPO method give you a Sharpe ratio of 0.96. If you apply it to a crypto portfolio of 8 tokens, some of the more liquid tokens, actually I have a typo. It should be June 2021. For that 1.5 year of out of sample backtest, Markowitz method give you a Sharpe ratio of 0.26. CPO give you a Sharpe ratio of 1. For a particular ETF, we have done a proof of concept on this ETF called MASH. It is a Canadian ETF, by the way. It is managed by a company called Evolve. It has a portfolio of 24 stocks that are traded on the US exchanges. But the interesting thing about this portfolio is that it is constrained to be long only. And in particular, the stock weight is between 0.5% to 10%, because most practical portfolios, we are not allowed to overly concentrate on specific one or two names. So we have to apply this constraint. So it become a more complicated problem. It's not just an unconstrained optimization problem. It's a constrained optimization problem. And again, for 1 year out of sample backtest, the Sharpe ratio in a bear market is 50% better than what the equal weight method generate. And most interestingly, CPO was able to adapt to the regime rapidly. In 2021, it was running a bull market portfolio, concentrating on growth stocks. In 2022, it automatically switched to a much more defensive portfolio. So even though it is still a negative Sharpe ratio, and that's mainly because of constraint. If we are running an unconstrained optimization, it will be positive. But because of the constraint, we are forced to allocate money to stock that we know are not going to perform well. But even with that constraint, we are able to reduce the loss by 50% in 2022, taking a more defensive position. And we have a client called WSG. They trade a Forex, is a Forex-based prop trading firm. They run a portfolio of 7 Forex strategies. And the constraint, again, is that they don't want to short their strategy. They only want to long it. And however, they also don't want to put more than 40% on any one strategy. And the outcome is, once again, quite remarkable. Compared to the existing equal weights method, it improved it almost 100% in terms of Sharpe ratio. And comparing even with the Markowitz method, it improved the Sharpe ratio by a significant 19%. So this method is, the numbers that we presented were based on backtest, out of sample backtest. However, they actually been deploying it live, and the first month result was, perhaps we were lucky, it actually doubled the P&L over the equal weight method. So you could, obviously it's only one data point in live trading, but it was gratifying that it didn't do anything crazy when you run it live. And there's another client that has a stock portfolio that he presented to us, 7 US and 2 Canadian tech stocks. The constraint is, again, he does not want to short any stocks, and he does not want to allocate more than 25% on any individual stocks. And the out of sample performance is that the Sharpe ratio and also the compound annual growth rate are both higher than the equal weight portfolio by 75%. Now, as you see, the complication of this method are twofold when you're trying to implement them. One is that there's the curse of dimensionality. How to overcome that is one of the really the great achievements of our mathematical team. The other is that to impose many constraints. So this is a lot of times a problem of dealing with constrained optimization. So for example, you might, instead of constraining the weights, you might want to say that you want to impose a minimum ESG rating on your portfolio, or you might want, or in terms of objective, you can say you want to maximize the ESG rating of portfolio instead of Sharpe. So the objective doesn't have to be returns or Sharpe. It can be anything you want, and the constraints indeed can also be anything you want. And our technical team has also provided this, is putting this together as a product offered via our API, so that client can experiment with different constraints and different objective functions at their own leisure, so that they don't have to depend on us to find out what's the optimal portfolio that they want, they desire. So as I said, all these are only possible because of our research team. Sergey, Sudarshan, Hao-Yu and Quinton. Most of them are mathematicians, and there's also significant interesting contribution by Gui, who is our summer intern from UC Berkeley. He was getting his PhD in optimization, and he also contributed some unique insights. It is truly a very exciting international and team effort to get to where we are in terms of the technique development and deployment into the actual product. So thank you very much, and I hope that I have left enough time for questions. I see that there are already some questions. So there's one question from Salim, is that he has been using Bayesian optimization for strategy parameters, and how is that different? Well, the main difference is that one major difference is that typically if you are using Bayesian optimization, the number of parameters are not huge. If it is of the order of hundreds, it might take a very long time. And secondly, typically Bayesian optimization does not take into account the external features as part of the optimization. So for example, Bayesian optimization is used very often in hyperparameter optimization for machine learning. But when you do that, the features are not used at the same time as the hyperparameters. The hyperparameters were not promoted to features, or another way to put it is that the features are not downgraded to become parameters as part of the optimization method. So they are separate in the optimization set. Oftentimes, you already have built a machine learning model. You already have used the features to make prediction while you are doing the hyperparameter optimization. So that's quite different from CPO method. So Mohammed has 4 questions. I think that the first one is, what is the lowest time frame? Lowest time frame is very much a function of how good your computer is. So if you have a very high performance computer, the inference step can be done in a second. That's not a problem. The training is what's taking longest time, because the training you really have to naively, you would have to find all combination of historical parameters for every time period for the training, right? So that could take a long time. But the inference, all you need to do is to make several hundred predictions. And again, because of our optimization technique, you don't need an exhaustive search. So inference can take as quickly as 1 second to generate the optimal parameter, depending on how powerful your computer is. Second one, in normal conditions, how fast your app code run? Well, I think it's a very similar question as the first one. How fast it can run depending on the computer. If you are running it on our server, we typically are dealing with portfolios that do not rebalance every second. We are dealing with portfolio that rebalance every week or even every month. So that's not, we are not optimized for high frequency trading, if that's the question. And yes, is the code run on premise or in server? Typically, it's run on our cloud server, but for institutional clients who want to have this code run on premise, that can be done. We are, just going to have a Dockerized version of our system that can run on your premise server. It's not a problem. As long as we have access to that server for data feeds, that is fine. And to test our app, I think Eric would be able to answer that. How can people try the method?
Yeah. So there's 2 ways. If you want to kind of actually specifically discuss it, you can book a call through our website, and we can go through and talk about how to specifically apply it to your portfolio. Additionally, if you send us an email with maybe the instruments in your portfolio, we're also able to quickly do it on our end and then send it back to you to give you some initial test results with our CPO product. So whether you want to actually discuss it, you can book a call, or if you're just interested in maybe seeing what the back test looks like, reach out to either info@PredictNow.ai or Eric@PredictNow.ai, and I will get back to you with some results.
I see that there's one of the participants has raised his hand. So yeah, feel free to type your question in the Q&A board if you have a question. You actually don't need to raise your hand. Just go and type in the Q&A board. That'd be good. So there's an anonymous person asks, does the client need to provide the features data in addition? No, you can if you want to, but we have created hundreds of features, both in traditional as well as in crypto space, that can be used for this optimization method. But of course, if you believe that you have created some special features that are particularly useful for this optimization problem, you can merge with our own features.
Yeah, just to clarify, to begin testing, all you really need to give us is the symbols of each instrument in your portfolio, and then we can use the public data to basically test it. But yes, as Ernest said, if you have your own input data that you would like to merge with our input data to basically have a more thorough model, then we can definitely accommodate that as well.
Yes, and for those who are afraid of revealing your trade secrets to us, those features that you provide to us, you do not need to name them. It will just be a time series. We would have no idea what they are. So you can merge it automatically using our API to our own features for even better optimization result. So yeah, so if you have missed the initial part of the presentation, I believe that the recording will be available. Is that correct, Eric?
Yeah. So if there's no more questions, feel free to, we have 15 more minutes. So if anyone has any more questions, feel free to ask. But yeah, if not, yes, we will be posting this recording to YouTube probably tomorrow. And I will also be sending a email with the link to everyone who signed up on Zoom and through our website. So basically, if you registered for this website, you should receive an email either tomorrow or Monday with a YouTube link where you can either rewatch or kind of distribute to any colleagues who you think might be interested in this technique.
Yeah, there's a number of other questions as well. Do you do a particular shrinking to the covariance matrix? The result presented so far requires no input from the covariance matrix, interestingly. So as I said, we do not need cross-sectional features in this methodology, quite in contrast to traditional techniques or other ML-based techniques. No cross-sectional features are needed. Covariance matrix is certainly a cross-sectional feature, right? Because you obviously need a number for every pair of instruments, but that's not even needed as an input. So yeah, that no shrinking is that needed because we don't even need the covariance. And Jeremy said, great show, thank you. Thank you for your attendance, Jeremy. So I think that is, if there are no further questions, I want to thank everyone again for your time. And as I said, as Eric said, recording will be available.
Yeah, thank you. And yeah, we'll give, I guess there's no more questions. We'll give you all 15 minutes back of your day. And thank you for attending. And if you have any specific questions, don't hesitate to reach out to info@PredictNow.ai, and we will be able to answer any questions or inquiries you may have.